Nationally known theoretician, particularly working in nonlinear photonics, but he's also built up a very strong research group which does not only theory but also experiment, and you'll hear of both those activities during his talk. Thank you, Yuri.
Thanks for inviting me, particularly Ivan and some other people from Sydney. We don't have our students. Somehow it was hidden from us for some time, and then it was late to arrange because I don't remember there's many other meetings. Anyway, you see two subtitles. So basically, it's a not equally distributed material, and the metamaterials. I will repeat some of the issues which Ross discussed this morning. But first of all, I want to say that I come from Nonlinear Physics Center. This is an Australian National University Research School of Physics and Engineering. Oh, sorry.
We are doing webcast and the sound would be not too good.
Let me find out why it's not working.
How about this one?
I should. Sorry, it doesn't move at all. It's probably after UST. Oh, no. It was shown that USB has a virus. But it's hard to stay there because I don't. Oh, okay, I see my screen. So I first the Nonlinear Physics Center. You mean that's much better. It's our center our center is the Australian National University. We have basically 5 research groups. They're all under the big umbrella of nonlinear physics, not nonlinear dynamics, nonlinear physics. And basically we have 2 groups working on nonlinear photonics. These are leaders of the group in experiment and theory, and this we are part of CUDAS. You probably know about CUDAS more than some of the people here know. Then we also have links to another center of excellence, an Atom Quantum Optics Center, AQUA, also established simultaneously with CUDAS. And we still have 2 more groups. Yes, metamaterials, theory experiment, and we have single-aligned optical vortices. We have a lot of links with people around the world because we cover many different activities. So today I will be talking about some of these activities associated with this group. Ilya Shadrivov is a group leader. He just last year got Queen Elizabeth fellowships here in Australia. So we cover different fields, we can interact, and that's why we try to build our success on interaction between different groups. Currently we have 9 research fellows, 5 postdocs, 11 PhD students. If some people want to join us, please contact me by email. I was not told about advertising. So what I'm going to talk today, I will talk about again about negative refraction, trying to make a kind of repetition from Ross's messages. And I will talk about how actually create metamaterials showing different structures. We'll talk a bit about tuning and about our favorite topic, which we actually generated several years ago, creating nonlinear metamaterials. So metamaterials is nonlinear response. And at the end, I will make a few comments about plasmonic waveguides and more recent hot topic of so-called nanofocusing. Of course, this is a nicer version of, I should be, nicer version of what already Ross presented. That's actually originally appeared in Veselagos' paper. And you see that normal materials were characterized by both positive epsilon and mu. And it's all come from definition of actually waves or wave number. For propagating waves, we have epsilon negative. I think Ross had epsilon negative here, but anyway. This is metals, materials which have negative epsilon. And then there are two waters which actually do not fit to any material known in the world, and they are basically associated with negative mu. And this is, as Ross explained, is a problem to actually make mu negative. So Bressilado came with the idea that basically you can look at this quarter, and with both negative, we can judge that waves will propagate in this medium. So this medium with both negative epsilon mu can somehow fit to our world, which surrounds us with electromagnetic waves. And he tried to pose the question, what would be this world with this unusual waves, and what will happen around us? People called it left-handed metamaterials. Actually, Bressilado first called it left-handed metamaterials, so our world is right-handed world. This is a picture of Bressilado, and actually people who are familiar with Russian literature will immediately recognize that something wrong in this reference. Why? Because Soviet physics uspekhi, it's like a Scientific American, kind of Scientific American. Do you take seriously papers published in Scientific American? Probably not really. Yeah. That's exactly what happened with him. The paper was rejected from the very strong, serious journal as a paper about nothing, because these materials do not exist. And then it was published because he knew one of the editors will publish in Uspekhi, it's called in Russian Uspekhi Fizических Наuk. It's kind of overview and some kind of general comments. It's not a journal where you can find serious papers, about science. But nevertheless, it was published, and then he discussed many of the issues which later Henry emphasized this lenses. But why it's left-handed? Basically, if you look at the normal electromagnetic waves, you see that electric field, magnetic field, and the Poynting vector, we basically create a triangle, and the propagation vector, wave vector is directed along the Poynting vector. So this is a very typical situation, and this is a kind of right-handed triangle, and that's why all normal materials are right-handed. For left-handed materials, we have opposite situation. We have K directed opposite to direction of Poynting vector, and this is kind of left-handed triangle. So you see that basically this is reverse triangle here, but most important here, which I believe Ross did not mention because of lack of time, is that because K and S oppositely directed, we have basically an interesting situation when for such materials, by definition, as soon as we assume epsilon negative, mu negative, group velocity is opposite to phase velocity. And this is so-called backward waves, which are known in physics, and this is basically reasons for negative refractions to occur. So negative refraction, as I want to show here, it's a textbook type problem, which we have the Snell's law definition angles. This is a way actually to present transmitted wave with a negative angle here. And in order to make this definition right, as Ross mentioned, we need to introduce minus here. So basically taking square root from n squared, we should have a plus and minus is exactly correspond to negative refraction. But negative refraction, it's not associated with left-handed materials. So somehow, on left-handed materials, this is a given property. But negative refraction, this is a very common physical phenomenon which was noticed some years ago. One of my, just as example which I have, actually I don't remember where is still that movie, but somehow it was not shown by Ross, but I have my own, but it doesn't show actually that nicely. So basically this is a way how, this is FDDT simulations of two materials, glass and air. You see that it's just opposite as I mentioned in the schematic diagram. So negative refraction actually it's an interesting physical phenomenon, and it's maybe viewed as a group in Germany tried to present by simulating difference between normal refraction and left-handed refraction. So in normal refraction, you know that if you put a stick in glass and put water, there is some refraction effect here, so stick looks shifted slightly. But let's imagine that we invented left-handed water. What will happen? This is what will happen. But the point is that we don't have left-handed water yet. But it's very common phenomenon. Actually, it's kind of a much broader class of phenomena in substances. So this is this diagram I show. This is materials with negative refraction, and we're inside of this big variety of materials. We have left-handed materials which sit inside. For them, all refraction is negative. But immediately question is, what kind of material should have this interesting property of negative refraction? As Ross mentioned, photonic crystals, also anisotropic media. Actually, initially it was a lot of mess in definition of left-handed materials. People, actually even in PRL was published papers saying, oh, we found new left-handed materials, but that was just negative refraction coming from anisotropy. But most interesting thing is that it's many people who study waves for a long time, they actually notice that. And I'm not sure how many people may understand Russian, but here, anyway, it's Mandelstam. It's a great guy who studied waves. It's not that part that he wrote in his lectures about waves, published in, it's a volume 4, I think. In 42, that there is nothing special about that case. It's just like, this is like a consequence of the only fact that group velocity and phase velocity are oppositely directed. So left-handed and metamaterials have nothing to do with these properties. In fact, our friend Professor Alan Boardman from Manchester took a more serious step to investigate who was the first who actually mentioned backward waves. And actually he found that in elasticity, Professor Lamb was both from Manchester, mentioned it in his papers about elastic waves. He discovered that there is a possibility when group velocity directed opposite the phase velocity, and then it was picked up by Schuster, who was already playing with electromagnetic waves. So basically Schuster was the first to introduce this backward wave for fewer electromagnetic waves. Now, unusual lenses means that we basically, if you have a left-handed materials, we can create the image from the flat slab, and that was already mentioned in '68 by Professor Veselaga and then picked up by John Pendley. Of course, it was a lot of discussions if you can create this perfect lens, and Ross, I realized that I know number of citations from Veselaga paper. It was last year, it was 2,300 or something like that, because I participated in nominating Veselaga for OSA award. So what is the idea of John Pendley? Why it was interesting in terms of this imaging and perfect lensing is basically the following sketch. In normal lens, when we start from the source, different waves propagate, but along with propagating waves, there are evanescent waves. Evanescent wave is a waves which decay from the source. If we decay from the source, basically we enter the lens with a very small amplitude and they disappear before image is reached. This means that evanescent waves do not participate in formation of image. That was well discussed by Ross. If you have left-handed materials, we have a kind of opposite situation when evanescent waves, it comes to the boundary and get amplified. Then, in many cases, people say, oh, it's impossible because you do not introduce gain in the system. You do not introduce loss, gain, you assume that everything conservative. But how can you get wave amplified inside of this metamaterial? This is somehow one of many tricks which metamaterials do to us. I will mention a few more. One of the tricks is the following. When you solve equations, these are usually for wave propagation, these are usually equations of second order. If you're talking about propagating waves, you write E, I, plus, minus, kx, right? You take two signs, plus and minus, and create cosine, sine, whatever. But when you're talking about decaying waves, what you usually do? You take minus kx, because waves should decay. You say, oh, who will take these growing solutions? We don't need that, because energy is not conserved. But in metamaterials, you should take two exponentials. When you make right matching, you will get growing exponents here. It's conservative system, but it's evanescent wave with the opposite sign of exponent. So that's what we should take into account when we're dealing with metamaterials. Due to this fact that basically the wave switched to growing exponential, then we get effective amplification waves inside of metamaterials, and basically images created outside, as was explained by Ross. Now, how to make metamaterials? Ross did not explain that, but I'm dealing with experimentalists every day, so I now should try to understand how to make it, and actually we have a lot of different structures in our lab. So we look at the response of magnetic ring, of metal ring, for example, gold ring. Basically, if you apply magnetic field, you have a current. Current, of course, can generate magnetic momentum. That's well trivial, it's from textbook. What was genius of John Pendry in a long time ago when Ross sold that paper, one of the first papers, he somehow got to the point when he decided to cut the ring. And that's actually breakthrough. Breakthrough is that if you now apply varying magnetic field, you find some regions near resonance associated with this ring, with the magnetic resonance of this ring, when you can reverse magnetic momentum. So basically you create a micro element which has a negative response. If you have a single micro element with negative magnetic response, you may think about generalizations, homogenizations, and type of structures which you can actually play with. But this is a key element, and basically when people realize how this magnetic electric response interact, came to ideas of different type of structures. So it's too early to ask if we can produce massive amounts of metamaterials, because we don't know exactly what we will be producing in 2 years. Anyway, this is we call split ring resonator. That was a great invention, and actually that was the basis of all metamaterials which we demonstrated at microwaves. Believe it or not, this is the first metamaterial created in San Diego by a group of David Smith. And basically, that's very funny because it's almost as big as this one. It's macroscopic for microwaves. Basically, we had the lattice of this double split rings. So we are double not because we need to, but because we wanted to make kind of a more isotropic response with cuts directed in opposite direction. Then a set of wires which produce negative epsilon. And the big miracle which happened here was that if you have these two systems, magnetic and electric, with both responses negative, these responses are negative only in narrow intervals. And basically the first structure which we fabricated actually corresponded to this case when both epsilon and negative overlaps. And this is kind of mystery. And David actually admits that that was pure coincidence. Because next structure we made, maybe not the second one, the third one, was completely wrong because it gave negative refraction for periodicity, from higher order diffraction patterns. So we published later these results of negative refraction, measuring it at n minus 2.7, comparing Teflon with the structure which we fabricate from these split ring resonators. These are different type of structures which people generated soon after, and this is a remarkable picture because it was fabricated by Boeing Corporation when basically DARPA in US actually ordered it to verify all these crazy theories. Theories come from science and physics of letters and put it on the military ground to make it useful. This different type of structures people produce, and this you see that they becoming smaller and smaller. This is 50 micrometers. And then it was kind of rush for smaller wavelength. Of course, terahertz is much easier to do because it's just downscaling. But then it was kind of stuck here because it's not easy to actually go to optical metamaterials. And not easy to go to optical metamaterials because you can't downscale the structure. There is some kind of physical limit, and then there is also physical limit that you can't actually operate with electrons in such a small structure. So it should be qualitatively new type of structures. And then it was a kind of breakthrough which occurs from different groups, suggests different type of new structures. One came from Shalaev's group, who used pairs of nanowires. But finally it was established that the most efficient type of structures which has both negative and epsilon, both epsilon and negative, is so-called fishnet metamaterials. These are like a lattice, where this waveguide or stripes that have different widths, narrow and wider. Basically, it's related to kind of plasmon resonances coming from these holes. It's a long story to actually explain why it's suitable, but so far the most efficient results for metamaterials are associated with this kind of structure. This is probably one of the latest development from John Group. I think it's something like, it's a sketch, up to 17 layers of this, it's what we call three-dimensional metamaterials, but because first lecture it was a question about cost, that sample was $5,000 US. So definitely not for mass production. It's only for nature paper. So many people try and struggle with different type of structures, and the most recent developments, which I want to show, it's already take advantage of coupling between magnetic and the electric field in the so-called spiral structures or chiral structures, which I will be probably mentioning on, I think, at time. So we fabricated, of course, we fabricated microwaves metamaterials back maybe 4 or 5 years ago, or even more, and did a lot of experiments. I will mention them, but really optical metamaterials was fabricated last year. That's typically fishnet structure, but we also try to measure responses to different tilted structures and trying to compare actually what will be results coming from negative index and also from so-called enhanced transmission coming from the resonances with these holes, but it's a long story. This is what I mentioned, the chiral metamaterials is the freshest idea, because basically what we have in metamaterials, as Ross also mentioned, we need kind of the interplay between magnetic and electric response. And chirality, the spirals, this particular structure fabricated by Wegener groups in Karlsruhe, the basically chirality allows to actually couple electric and magnetic field. And I think it's last year several groups reported observation of negative index from chiral structures. This looks like a very promising direction, because in that way we can fabricate structures with low losses. Otherwise you need to involve metals, like in copper with first microwave experiments, or silver and gold, and they are very lossy. We have plans in Kudos for next extension of Kudos and Spinboom. We have all facilities, we basically unique facilities of Wegener's group, and we already have some first results in collaboration with Professor Mingu about fabrications of chiral metamaterials in the way which group of Wegener fabricates. Now, the different properties of metamaterials, which we may discuss many times in different type of approximation. One of the first ideas which we had, just let's take a slab of metamaterial, look what will happen. When you solve Maxwell equations for guided waves, it's a relatively trivial exercise which can be found in textbook. You find waves which decay from the slab because it's kind of waveguide, but now waveguide has a negative index. And as soon as you find different modes, you try to solve kind of transcendental equation, like for usual waves, and then you realize that in this waveguide, left-handed, right-handed, right-handed, we don't have fundamental modes. Fundamental modes are like a bell-shaped profile, lower order mode, which is guided by this waveguide. So there is no fundamental modes, and the lowest mode has these two peaks. It consists of two surface waves, and this is with the in phase and out of phase. People who are familiar with plasmonics, which with surface waves or surface plasmon polyritone, will recognize that these are very similar object like surface plasmon polyritone. This is kind of one surface wave, the second wave, surface waves, and guided mode consists of these two such surface waves. So even this one already shows that there is a link between plasmons, waves which exist at the interface between dielectric and metal, and this negative index metamaterials. Because in usual metals we have only epsilon negative, but it's already enough to reproduce many properties of metamaterials. What is interesting here, even it looks very trivial problem, if you, as I mentioned, that power flow in metamaterials can be oppositely directed. So basically, we may have situation when energy flows in the outside of waveguide and inside of waveguides. It's actually directed opposite to energy flow inside of the waveguide. So basically, we have a very non-trivial situation how we can build this type of surface space. And the answer is that all the surface space are actually vortices. So if you study, for example, a mirror, on a mirror, you can understand that because it's metal, basically, if you have some excitations around the mirror, there should be also vortices, because this vorticity comes from the properties of epsilon negative. Now, you can discuss many different tricky properties of that metamaterial. That's why people got interested, because as Ross mentioned, basically every property, physical effect, so a physical property, you know in physics, you try to change sign of mu and see what happens. That's why you see the different type of reverse effect, reverse Cherenkov, whatever. What is interesting is that people did not pay much attention that mu can be negative. So some formulas which you can find in textbook, they don't have mu at all, because mu by definition is assumed to be 1. So if you want to change formulas, it's not that easy. You need to derive them to have mu inside. But this is very, I have basically one example which I like very much to show you what is the difference between metamaterials and normal materials. We have two slabs, and we have a waves which propagate through two slabs. What we know exactly, we know that there is a kind of resonances, because wave actually is scattered from both the slab layers. And if you take many, many layers, we should have a break scattering resonances. This is a condition when difference between two phases is just integer 2 pi number. This comes from different type of textbooks. If you have one layer left-handed, we basically have a different situation, because in usual case, we have phase of the wave advance, and left-handed we have phase of the wave delay. So basically, we may compensate completely phase shift. So basically, we can have a non-resonant reflection when total phase vanishes. This is one of the properties of these left-handed materials, and people try and build interesting developments, and actually transformation optics uses this type of properties. But what happens if I take a periodic structure? If I take a periodic structure of right and left-handed materials, and we discover that in addition to the famous break conditions, break reflection condition, when we have a resonant this periodic structure, this is valid for any type of waves, electromagnetic, sound, whatever. We know that if you have a periodic system of elements, we have so-called resonant reflections and photonic band gaps. It's just one of the cases. But now, because index of left-handed materials is negative, we may satisfy this simple condition. Basically, the sum is not integer of 2 pi, just 0, because index of left-handed material negative. So this means that in that way we found a new type of break resonance, or break resonance satisfied when n equals 0, which is not possible for right-handed materials. But if you go one step further with this one-dimensional system, we discover even more fascinating property. So what we know about this one-dimensional photonic crystals, this is a kind of periodic structures which we call usually band gap material photonic crystals. We know that if it's one-dimensional periodicity, wave has a band gap in transversely to periodic structure. So if I propagate wave in that direction, then I can satisfy break condition. If wavelength satisfy break condition, we can break band gap. But if system has one-dimensional periodicity, we can always propagate waves along that direction. But somehow it's understandable, it's like a given that, of course, as long as there is no periodicity, no reflection, we can propagate in that direction. But it's true if every material here is positive, it has positive n. If one of the materials has negative n, we completely change the picture. Why? Because we basically find that in such material, we can have a complete band gap. So wave may not be coupled to waveguides, it may not be propagated. So you go to analysis of the structure through this usual Floquet theory. You write your eigenvalues. This is KB, comes from periodic structure. Then you study propagation for TE, TM modes, and you find the so-called complete band gap. So one-dimensional system may have a complete two-dimensional band gap. This sounds like complete nonsense. But because of left-handed materials involved, that become possible. And then you, of course, should go backward and see what is the physics of all this coupling with this one-dimensional structure. So physics is the following. You have a source which is placed near the structure, and then source generates a kind of FDTD simulations. Source generate waves, and then waves comes to interact with one-dimensional structure. What happens? If it's usual material here, basically waves penetrate through this material, they couple to the layers, and they propagate along the layers. This is what everybody understands from conventional theory. So if source is placed near material just allows they propagate. Of course, no losses, everything is transparent. Now, if it would be band gap, as we have in this system when left-handed materials are involved, all waves are reflected, meaning that there is no wave propagating inside. And this is a case which we found. Basically, if every second layer will be left-handed at negative index, we can have that interesting property. And this is partial gap when we couple to surface waves along the surface. So what's happening here? There is a case when this periodic system can't actually couple to external source. There are no waves propagation along. That special condition, of course, if you look at the mu here, so it's mu is in a particular range for these parameters. But it actually explains that you can use one-dimensional structure and compose a two-dimensional band gap material only with one-dimensional structure. So what happened in there, outside of that region, we couple to Bloch waves of the structure. So this is transversal waves which exist in periodic system. Outside of that region, from the other side, we couple to this guided walls of this one-dimensional system. But there is a region of that structure when you don't couple to anything. You don't couple to Bloch waves, and you don't couple to guided walls. This is impossible for these conventional materials, but it's possible with negative index materials. So in that region, we have exactly two-dimensional band gap because source play there doesn't allow any waves to escape from the structures. So it looks quite controversial, but after we published with big problems, because referee just basic argument of referee was this is impossible because this is impossible. And then some people actually look at different structures, at the metal dielectric structures, when not instead of left-handed material, we have just metal structures. And I mentioned that metals very often behave like negative index materials, even only the one epsilon is negative, but we also found conditions that we can get this two-dimensional structures, or one-dimensional structures behaving like two-dimensional band gap materials. I just finalize this slide and we can make a break. Our goal all the time was to create tunable metamaterials, and this is now a goal of many groups because we learn how to fabricate some structures, we measure basic properties, but we want to get some functionalities of these materials. To get functionalities of these materials, we call them, we need to make them tunable. Tunability means that we should actually get resonances, remove resonances. So basically the element for metamaterials is a kind of simple LC circuit or splitter resonator. So what we can do, we basically can introduce different type of ways to control this frequency of magnetic resonance. What we can do, basically magnetic resonance means that we have some dip in the transmission from the system of this splitter resonators. So this is a way we basically we implement it in our group. We introduce some elements here, which is actually varactor. A varactor is a unidirectional diode. and it changes properties when you apply either DC voltage or just you change power of your source. If you have reactors, you have concentration of field there, I will explain in a second, and then you may control this resonance. Basically, this is that way. You can control resonance by shifting. You can introduce different type materials. People try to introduce in quantum dots and so on. You can change substrate where this structure is located. You can basically take different substrates or just infiltrate structure with liquid crystals, or with put substrate nonlinear. You can basically tune in that way resonance. You can also change this substrate mechanically through different type of actions. And in that sense, we can basically also employ this way of controlling this, either it's resonant or just no resonance. This is results, the theoretical results we published when we just introduced liquid crystals in holes of this fishnet structure. And we show that obviously using two orientations of molecules, of elongated molecules of nematic liquid crystals in these holes, we can basically tune our response, particular effective refractive index, from positive to negative just by swapping, by applying a different electric field. So basically there is tunability which is proven theoretically, but shown so far was tunability of metamaterials through temperature tuning of liquid crystals. When you just, by changing temperature, you change the refractive index of the structures. This is what I explained. Now, then we can basically stop here and I can answer questions or make a break and then continue in 5 minutes, okay?